Welcome back to Mindcast. I'm your host, Will. Today we're diving into one of the most intriguing questions in artificial intelligence. Can we create better AI by essentially throwing architectural spaghetti at the wall and seeing what sticks? I came across this incredible research paper titled Architectural Darwinism or Computational Profligacy. A mouthful, I know. But it tackles a deceptively simple idea. What if, instead of carefully designing AI systems, we just randomly modify them and test thousands of variations? It sounds almost too simple to work, but that's exactly what makes it so compelling to examine. Before we can understand why random modification might not be the golden ticket, we need to appreciate just how sophisticated modern large language models really are. We're not talking about simple programs here. We're talking about architectural marvels that are the result of years of cumulative research. Think of a modern AI like GPT-4 or Claude as a Formula One race car. Every component, from the transformer architecture to the attention mechanisms to the feed-forward networks, has been precisely engineered and tested. The self-attention mechanism alone is a masterpiece of mathematical elegance, allowing the AI to weigh the importance of every word in context with every other word simultaneously. And then there's the mixture of experts architecture. Imagine having not one expert, but 8 or more specialized experts, each handling different types of problems, with a smart routing system deciding which experts to consult for each question. It's like having a team of specialists working in perfect coordination.
So here's where the plot thickens. Some researchers have proposed what sounds like a reasonable approach. Why not create thousands or millions of variations of these architectures by randomly modifying them, train each one, and see which performs best?
It's essentially artificial evolution, just like how nature supposedly created the incredible diversity of life through random mutations and natural selection. The idea has this appealing simplicity: let the computer do the hard work of design for us. But here's what's fascinating. This isn't actually a new idea. What we're describing is essentially neural architecture search, or NAS, which has been around for decades. And here's the kicker. The research community largely moved away from random search methods years ago because they were brutally expensive and inefficient. Early NAS methods were exactly like this random approach. They were evolutionary algorithms that would create populations of neural networks, test them, select the fittest, and breed new generations. But researchers quickly discovered that you needed to evaluate thousands upon thousands of candidates to find anything worthwhile. Think of it like this. If you were trying to improve a Formula One car by randomly swapping parts, you might eventually stumble upon a better configuration, but you'd probably create thousands of cars that couldn't even start, let alone win races. This brings us to one of the most important discoveries in AI research: neural scaling laws. This is where things get really interesting, and frankly, where the random search idea starts to fall apart. Researchers at OpenAI and DeepMind made a remarkable discovery. The performance of language models follows predictable mathematical relationships with 3 key factors: the number of parameters in the model, the size of the training data set, and the amount of compute used for training. These relationships hold across more than 7 orders of magnitude, from tiny models to giants like GPT-4. But here's the crucial finding that undermines the random search approach. Model performance depends most strongly on scale and only weakly on other architectural details like depth versus width. In other words, within the transformer paradigm, the specific arrangement of components matters far less than simply making everything bigger. It's like discovering that the secret to a faster car isn't in tweaking the precise angle of the spoiler, but in putting in a much more powerful engine. Now let's talk numbers, because this is where the random search proposal goes from questionable to absolutely absurd. Training a single state-of-the-art language model today costs between $50 million and $200 million. That's for one model. The paper I'm discussing estimates that training GPT-4 cost around $78 million, while Google's Gemini Ultra may have cost nearly $200 million. Meta's Llama 3 reportedly required a cluster of 24,000 high-end GPUs. That's $720 million in hardware alone before you even factor in electricity, cooling, storage, and the small army of engineers required. Now, remember that effective neural architecture search typically requires evaluating thousands of candidate architectures. Let's do some sobering math. If you wanted to properly search the space with just 1,000 candidates, and that's being extremely conservative, you'd be looking at $50 to $200 billion. That's not a typo. We're talking about more money than most countries spend on their entire military budgets. Here's where we encounter what I call the innovation paradox. The random search approach confuses optimization with innovation. True architectural breakthroughs, like the original transformer, or newer approaches like state-space models, didn't emerge from randomly shuffling existing components. They came from deep, principled thinking about fundamental problems. Take Mamba, the state-space model that's generating excitement in the AI community. It wasn't discovered by randomly modifying a transformer. It emerged from researchers who understood control theory and realized they could replace the quadratic complexity attention mechanism with something linear, potentially allowing for much longer context windows at a fraction of the computational cost.
Similarly, diffusion-based language models are inspired by the success of diffusion models in image generation. Instead of generating text one token at a time, they treat text generation as a parallel refinement process, starting from noise and iteratively denoising it into coherent output.
So if random search isn't the answer, what is? The research suggests a much more nuanced approach. First, continue scaling proven architectures according to the established scaling laws. That's your guaranteed return on investment. Second, fund diverse research groups exploring fundamentally different paradigms at smaller, more manageable scales. Think of it as a portfolio approach. Put most of your resources into the reliable, predictable gains from scaling, while dedicating a portion to higher risk, higher reward research into completely new architectural paradigms. The goal isn't to find a slightly better arrangement of existing components. It's to discover entirely new computational frameworks where different, more favorable scaling laws might apply. As we wrap up today's deep dive, here's the key insight. In the world of AI development, we're not looking for better ways to arrange the deck chairs. We're looking for entirely different ships. The random search approach, while intuitively appealing, represents computational profligacy rather than Darwinian efficiency. It's a search for a needle in a haystack, where each piece of hay costs millions of dollars to examine, and the prevailing scientific theory suggests the needle, if it exists at all, provides only marginal improvements. True progress comes not from random tinkering, but from paradigm shifts driven by deep understanding of fundamental principles. It's the difference between randomly rearranging words, hoping to write poetry, and understanding the profound structures of language that make poetry possible. The future of AI lies not in rolling computational dice, but in the careful application of human insight, scientific principles, and yes, when appropriate, massive scale. Thanks for joining me on Mindcast today. Until next time, keep questioning, keep thinking, and remember, sometimes the most sophisticated answer is the one that helps us understand why the simple solution isn't so simple after all.